Hi everyone, this is lesson 1-7, inverse relations and functions. Our learning target for today is to be able to use the horizontal line test to determine inverse functions. On this slide we have two inverse relations, and a relation, just as a reminder, is a group of ordered pairs. So group of ordered pairs can be displayed in a table setting. And you have table A here, which is showing a number of tickets. We have number of tickets here, and then its corresponding cost. So if one were to purchase one ticket, it's a cost of $2, and if you purchase two tickets, it's a cost of $4. Three tickets would cost $6, four would cost $8, six would cost $10. So we can write these as ordered pairs: 1, 2, 2, 4, 3, 6, 4, 8, and 6, 10. Now in table B, we have the reverse of that, or what's called the inverse. Now, instead of tickets being the X value and cost being the Y value, those values are reversed, and now the cost, or the money spent, is X, and the tickets are Y. So we would have the ordered pair 2, 1, 4, 2, 6, 3, 8, 4, and 10, 6. And that is the inverse of table B, is the inverse of table A, because you notice that if you compare this ordered pair here with this ordered pair here, all we've done is reverse or interchange the X and Y coordinates. And that's what makes up an inverse relation. An inverse relation is when you take the ordered pairs in one relation or in one group, and you interchange or switch the X and Y coordinates, or you flip-flop them. Then table B represents the inverse relation of that first relation given in table A. If you notice that all of these pairs here, 2, 4, then the inverse function would have the ordered pair 4, 2. 3, 6 would then be 6, 3 in the inverse. 4, 8 would then be 8, 4. And 6, 10 would be 10, 6 in the inverse. The relation shown in table A is the inverse of the relation shown in table B. And to be more specific, by definition, inverse relations exist if and only if one relation contains B, A, and the other relation contains A, B. So what they're trying to tell you is what I was showing you in the last slide, is that the ordered pairs have to be interchanged, or the X and Y coordinates have to be flip-flopped in order for one relation to be the inverse of another. When a relation is expressed as an equation, its inverse relation can be found by interchanging the independent and dependent variables. Now, to review what independent and dependent variables are, generally speaking, an independent variable is going to be your X coordinate, and your dependent variable is going to be your Y coordinate. So if you think about what we were doing with the relations in the tables on the previous slide, when we have an equation, we're going to also flip-flop X and Y, just like we did in those relations on the previous slides. So what we want to do here is we want to look at, I've given you guys an example of a graph, and we're going to start with this as being our original function, f of x. We'll say f of x equals x squared minus 4. That's the equation that goes with this blue graph right here. And we graph the function x squared minus 4 on a standard window from -10 to +10 on the x-axis and -10 to +10 on the y-axis. And if you graph this yourself, you will see the same graph I have listed here. Now, looking at the ordered pairs, I've also graphed the inverse function, which is in red. And if you look at that, the reason why the red graph is an inverse is because if you look at the ordered pair, -3, 5, which is on f of x, that's on the blue graph, is an ordered pair, -3, positive 5. Then the red graph would have the ordered pair 5, negative 3. If those two functions are inverses of each other, if the blue graph and the red graph are inverses of each other, then any point that is on the blue graph should have its x and y coordinates switched, and that would be a point on the inverse, which is in red. Now, if you look down here at 5, negative 3, that is an ordered pair on the red graph. Therefore, we know that the blue graph and the red graph are inverses of one another. Now, another way to write f of x is, instead of using f of x equals x squared minus 4, we could say y equals x squared minus 4. And then we know that the inverse equation is just switching x and y in the equation. So my inverse equation for in red here would be x equals y squared minus 4. That is that's the equation for the graph in red. Now, in order to graph what I have in red there, because we know on the graphing calculator you have to have y by itself to type in an equation in our equation editor, I had to do some algebra and solve this equation for y in order for this red graph to show up on my graphing calculator. Now, if I'm going to go ahead and solve this equation for y, I would start by adding adding 4 to both sides, rather. So if I add 4, I get x plus 4 equals y squared. And then to finish solving for y, I would square root both sides to get rid of the square, and I need to put a plus or minus in front of my answer, which means that y equals plus or minus square root of x plus 4. Now, remember that anything with a plus or minus, you have to type in 2 separate equations into your equation editor. So in y2, I graphed the equation square root of x plus 4. And in y3, I graphed the opposite of square root of x plus 4. Hence why you have in y2 here, one column of y values, and you have another column for y3. If you put those two equations together, they make up the red sideways parabola that we have shown in the picture right here. Okay, so we have this sideways parabola, which is all of these x values paired with these y values would give you the top part of the parabola, and all of these x values paired with these y values right here in column y3 would give you the bottom half of this parabola. If you notice on the previous slide, we have another graph, another column there even in the table that's magenta. And we have this magenta line going through. That magenta line is the equation for y equals x. So that line y equals x is to show that a graph and its inverse are reflections of each other over that line. So if you took the blue graph and reflected every point on that blue graph over the line y equals x, which really, if you're reflecting over the line y equals x, what you're really doing is just switching the x and y coordinate. You're showing that one graph or one function is a reflection of another over the line y equals x. Now, this relationship is true for all graphs of relations and their inverse relations. So if two relations are inverses of one another, then if you graph both of those relations, they should be reflections over the line y equals x. Now, we are most interested in functions with inverse relations that are also functions. Okay. If the inverse relation is a function, then it is called an inverse function, not an inverse relation anymore. And typo here, it is denoted f of negative 1. This right here is the symbol for the inverse of f. And it's read f inverse. Okay, that little symbol f with a negative 1 means inverse. And if you had g with a -1, then it would be the inverse of g. So we're going to call the blue function here f of x, right? This was the label f, and we determined that the red function here was the inverse of the blue function, so we'll call the red one f -1, which stands for the inverse of f. Now, not every inverse is going to be a function. If you think about the definition of a function is going to have a graph that passes the vertical line test. So if you look at the blue graph, which is a parabola, does pass the vertical line test. However, the red graph, the inverse, does not pass the vertical line test. So we can say f of -1 is not a function when the blue graph, if you drew a vertical line through the blue graph, any vertical line through the blue graph is only going to intersect the blue graph at one point, which makes the blue graph, or the function f, a function. So f is a function because it passes the vertical line test. So just to summarize what we talked about on the last slide is that just because the graph of f is a function does not necessarily mean its inverse is going to be a function. And so we determined that given y equals x squared minus 4, which is the graph in blue, I'll highlight that in blue instead, the graph in blue, and then the graph in red here did not pass the vertical line test, therefore it was not a function. The main point of this lesson is to discuss the horizontal line test. The horizontal line test is used to determine whether a function f has an inverse that is also a function. In words, a function f has an inverse, f -1, if and only if each horizontal line intersects the graph of the function in at most one point. Okay, if you look at the graph here, there's a function in blue, f of x, and if you look at the horizontal line that they have provided, okay, the horizontal line here only intersects that graph at one point. Okay, because that horizontal line intersects the graph of f at only one point, we would say that function passes the horizontal line test, which means that f inverse is a function. In this example, f inverse is a function. I don't have to go through and find the equation or graph the inverse in order to determine whether it's a function. That's the point of the horizontal line test. The horizontal line test is used to show that without having to find the equation of the inverse or graph the inverse, that a function would have an inverse that exists and that it's a function. Now, to summarize this, if the graph of f of x passes the horizontal line test, it has an inverse that is a function. If f of x does not pass the horizontal line test, meaning that the horizontal line intersects the inverse in more than one, the horizontal line intersects the graph of f in more than one spot, then its inverse relation is not a function. To give you a better example, the graph we had on the previous slide, which was y equals x squared minus 4, if we tested that function using the horizontal line test, it does not pass the horizontal line test because that horizontal line intersects the graph of f in more than one spot. So therefore, just based on looking at the graph of f without even having to find the equation and graph the inverse, I know just by looking at f whether the inverse is going to be a function or not. That's because the graph does not pass the vertical line test. The graph of f does not pass the horizontal line test, so its inverse is not a function. In example 1, we're applying the horizontal line test. In A, graph the function f of x equals 4x squared plus 4x plus 1 using a graphing calculator, and apply the horizontal line test to determine whether its inverse function exists. Write yes or no. Now, if you look at the graph given, I have graphed on a standard window the function f of x equals 4x squared plus 4x plus 1. And if you look at the graph of the function and I apply the horizontal line test, I know that f inverse does not exist as a function. Okay? F inverse does not exist because the original function f, which I've graphed in blue here, does not pass the horizontal line test. The horizontal line intersects the graph in more than one spot, so f inverse does not exist. In example 1, we are going to be applying the horizontal line test, and in part B, we're given the function of x to the 5th plus x cubed minus 1. And we're going to use the graphing calculator to graph that and apply the horizontal line test to determine whether its inverse function exists. Write yes or no. Okay, so on this graph, right here, the graph, if I did the horizontal line test, don't be fooled by that little part. It is not horizontal or flat. So therefore, and you could tell it's not horizontal because you'll see in your table that your y value is not constant there for several x values. You get a different x value for every y value. And so to look at this, I would say that it passes the horizontal line test, so I would say yes, f inverse exists. The inverse function exists because the graph of f of x passes the horizontal line test. Under the check for understanding, we're given the graph of the function f of x equals 3 over x minus 1 using a graphing calculator, and we are asked to apply the horizontal line test to determine whether its inverse function exists. Write yes or no. So here's what you need to do. We have 4 choices, A, B, C, and D. In A, you're saying yes, the inverse exists, and this is the graph of f. In B, you're saying yes, the inverse exists, and this is the graph of f. In C, you're saying no, the inverse does not exist, that the graph given is f. And in D, you're saying the inverse does not exist, and that is the graph of f. I want you to go ahead and graph f of x equals 3 over x minus 1. Determine which graph is correct, and whether or not, based upon that graph, you can decide if the inverse is a function. When you are done, choose A, B, C, or D, and then press submit.